Professor Bialis here. In this video we're going to be talking about section 2.7, which is further problem solving. Basically what this is, it just takes the word problem applications that we talk about in this chapter, kind of throws them all together, bumps up their intensity a little bit, and then we just kind of keep practicing. Okay, there's only going to be 4 examples that I talk about in this section. As always, they're going to be found in the textbook. Practice 1. Can be found on page 141, and it reads, Satron took a short hike with his friends up Mount Wachusett. They hiked uphill at a steady pace of 1.5 miles per hour and downhill at a rate of 4 miles per hour. If the time to climb the mountain took an hour more than the time to hike down, how long was the entire hike? Okay, for something like this, we are dealing with distances, rates, speeds, and time. Now, this is not like if you saw the previous video where we had the lava flowing down the volcano. That was just a simple distance, rate, and time. Here we have 2 different scenarios. Okay, and pretty much all distance problems we see from here on out are going to have 2 scenarios. These problems cause a lot of headache for students because there is a certain level of complexity that we have to deal with. But if you do enough of these, you're going to see that they are very repetitive. So let's see how to start this out. So we have a distance problem. You may have to read it a couple times to get that, but we have a distance problem in this case. Whenever we have a distance problem, we are going to have 2 scenarios, and each scenario is going to have a distance, a rate, and a time. Make a table, okay? And it's going to be the same type of table every time. So first off, decide and identify that this is the type of problem we have. Then fill these in, okay? So let's go back. What are the scenarios? We've got Satron took a short hike with his friends up Mount Wachusett. So he's hiking. We don't need that anymore. They hiked uphill at a steady pace of 1.5 miles per hour and downhill at a rate of 4 miles per hour. So it's not 2 different people or 2 different groups. It's the same group going uphill and then turning around, coming downhill. Those are our scenarios. Uphill and downhill. Okay? Now, after that we start filling this in. I don't care if this is a introductory algebra class, intermediate algebra class, college algebra class, pre-calc class. If you see a problem like this, they will always give you one of these pieces of information. So they'll give you the distances or give you the rates, give you the times. They'll describe one of them, and then you're going to use those 2 to build the third. Okay? Let me show you what I mean by that. So let's look at this problem again. It says, they hiked uphill at a steady pace of 1.5 miles per hour. So uphill, they gave you that the rate is 1.5 miles per hour. They gave it to you. And if you read on, it says, and downhill at a rate of 4 miles per hour. They gave it to you. They gave you the rates. Okay, then we read on. It says, if the time to climb the mountain took an hour more than the time to hike down. That's the description part. The time to hike the mountain took an hour more than to hike down. So, downhill, I have no idea how long that took. But to go uphill, took 1 more hour. That's what I meant by they gave you something, they described something. Now, we are going to use these 2 to build the distances. Okay? They don't say anything about the distances. They say nothing about it. But we can say algebraically that the distance here is the rate times the time. And the rate times the time. Gave it to us, described it to us, we build these. Now, the thing that we build ourselves is typically what we're going to be using to make our equation. Okay? So again, if we go back to the problem, they say it took an hour longer. Then how long was the entire hike? That's all they give us. Okay? So we have to decide What is true about these distances? Did they say that they took a different route? They didn't. They went up the hill, they came back down. We have to assume that they are going up, turning around, and coming the same way back down. So the distance up should be equal to the distance down. And what that gives us is that. And now we have an equation to solve. So we've got distribution get the variable on one side, be careful, we've got 4 minus 1 is 3, minus a 0.5 is 2.5 t. And then we've got divide by 2.5 and then 1.5 divided by 2.5 is a 0.6. Okay? Now make sure you interpret, especially these distance problems, make sure you answer the question. They asked how long did the entire hike take? We just found t. That's the time they took to go downhill. But to go uphill was an hour more than that. So uphill was 1.6 hours. 1.6 hours up, 0.6 hours down. Add those up, and you have 2.2 hours. Solving the equation is great. You should feel a sense of accomplishment when you get to this point, but then stop and say, okay, what do I do with that? Okay, that last bit should not be a very cumbersome thing to go through, but we need to make sure that we're aware of it. Okay, so final answer, 2.2 hours for the entire hike. Okay, so let's go on to practice 2. Practice 2 can be found on page 142. And it reads, the Kansas City Southern Railway has a station in Mexico City, Mexico. Suppose 2 trains leave Mexico City at the same time. One travels east and the other west at a speed that is 10 miles per hour slower. In 1.5 hours, the trains are 171 miles apart. Find the speed of each train. Okay. Now, again, we're talking about distances, we're talking about speeds or rates, okay, and we're talking about a time. So we have, again, a distance, rate, and time problem. Remember, we have 2 different scenarios, each with their own distance equals rate times time. 1 or 2 read-throughs to decide that this is what we need to do. That's it. Now we have to decide what 2 scenarios are we talking about. Are we talking about uphill, downhill? In this case, no. We're talking about 2 trains. One went east, one went west. Okay, again, 2, maybe 3 read-throughs to get to this point. Expect that. And don't be like, oh, I don't know what I'm doing. It will take you a few times to get to this point. So be comfortable with that, expect that, and don't get stressed out about it. Now I start taking the values out. Remember, one of these categories will be given to us, one of them described to us, and then we combine those to get the third. So let's see what they tell us. Kansas City Southern Railway has a station in Mexico City, Mexico. Fine. Okay, suppose 2 trains leave Mexico City at the same time. Whenever they say something's the same, just remember that. Don't write anything down yet, but the same time they left. Okay? One travels east and the other west at a speed that is 10 miles per hour slower. Okay, one's going east and the other west 10 miles per hour slower. So the east speed, I don't know. But the westbound train is going 10 slower. That was what was described to us. I read on. It says, in 1.5 hours, the trains are 171 miles apart. Find the speed of each train. So what's happening is you have this train station, one going west, one going east. After 1.5 hours, they're 171 miles apart. What I see a lot of students do is they put 171 and 171. Be careful, because that 171 is not a distance covered by each train. That is a total distance. So I can't put 171, 171. But if they left at the same time and 1.5 hours pass, then they both were traveling for 1.5 hours. Okay? This 171 will come up again in a second. This was given to us. This was described to us. Distance is rate times time, and rate times time. Okay? Now, like I said in the previous example, this is typically where our equation's going to be found. Now, are these distances equal? No, because one's going faster than the other. Okay, so they can't be covering the same distance in the same amount of time. Okay, so what do we know about these distances? Together, they are covering a distance of 171. So what I would do is take the distance covered by the eastbound train and add to it the distance covered by the westbound train to get a total distance of 171. It's not always set these equal. This is where we have to think a little bit and add a little bit of a finesse to the problem. We know we're going to do something with these, but we have to interpret what needs to be done. And now I solve my equation. So I've got 1.5r plus 1.5r minus 15 equals 171. Combine like terms to get 3r minus 15. I add a 15. And I get 186. And then I divide by 3. R equals 62. And R we placed as the rate for the eastbound train. So that eastbound train is going 62 miles per hour, and that westbound train was going 10 less than that, so it's going 52 miles per hour. And there's your final answer. So guys, again, these are not, 3-second problems. They're going to require some thought, some time, but I want you to start seeing the consistencies. Something's given, something's described, pull those together to get the third. Once we build these, that's where we get our equation. The equation, what to build with those, is going to be described to us in the problem. Okay? Let's move on to something a little different. Let's go on to practice 3. Practice 3 is found on page 143. Let's see what this says. Okay, it reads, a stack of $5 and $20 bills was counted by the treasurer of an organization. The total value of the money was $1,710, and there were 47 more $5 bills than $20 bills. Find the number of each type of bill. So we're talking about something of value. Okay, now here we're talking about $5 and $20 bills. It could be tickets, adult tickets, kids tickets. It could be stamps, anything of value. I want you to think of this as a value problem. Okay. Now, when we have a value problem, there's two components. There's the value of what you have, and then the quantity of what you have. That's what we should be focusing on with these. Okay. So what we have are $5 bills and $20 bills. Now I talked value and quantity. We know the value of a $5 bill is $5 and $20 for the $20 bill. But the quantity of them is in question. So we have a number of and number of. That's what we're trying to describe here algebraically. So let's go back in there. It says we have a stack of 5s and 20s. Okay, the total value of the money is $1,710. So I know the total is $1,710. Okay. Now, then it says that there were 47 more 5s than 20s. 47 more 5s than 20s. They tell us nothing about the 20s. There's my variable. But there's 47 more of the 5s. So t plus 47. These are the pieces of the puzzle that we need to now put together. So this represents the quantities of each. This is a total value. Now where's that total value coming from? It's coming from a value of 5s and a value of 20s. The 5s, if I have 3 $5 bills, how much do I have? I have 15 because 3 times 5. This will have a value of $5 that many times. Plus the $20 that many times. Value times quantity, total value here. Okay? Now I just have this to solve. So I've got 5t plus, again, something like this, if you need, do that. That's a good practice. That's good exercise to go through. 7 times 5 is 35, 23, so 235 plus 20t equals 1,710. I've got 25t plus 235 equals that. Subtract the 235. $25t equals, again, if you have to, do some borrowing. That's good to practice. 10 minus 5 is 5. I'm going to do some borrowing again. 10 minus 3 is 7. 6 minus 2 is 4. So I got 1,475. Divide by 25. 25 going into that. 25 doesn't go into 1, doesn't go into 14, it does go into 147. 5 times. 5 times 5 is 25, carry the 2. 5 times 2 is 10, plus 2 is 12. Subtract. I got 22. Carry down that 5. How many times does 25 go into 225? 9. 9 times 5 is 45. 9 times 2 is 18, plus 4 is 22. And I got 59. Now remember, what did T represent? T represented the number of $20 bills. So there's 59 $20 bills. And then there were 47 more $5 bills. Okay, so 59 plus 47. There's 106 $5 bills. And there we go. Make sure you specify which is which. Okay? Some instructors are going to say they want a complete sentence with your answer. I'm not too big on that, not say it's bad, I would rather you guys focus on this. But at the very least, specify which is which. Okay? And that's practice 3. That's again a value type problem. So we've talked about distance problems for a couple examples. This is a value type problem. It could be bills, it could be coins, stamps, tickets, anything of value. And now let's go on to our last example. Our last example, practice 4, can be found on page 144. And it says, Suzanne Scarpula invested $30,000, part in a high-risk venture that yielded 11.5% per year, and the rest in a secure mutual fund paying interest of 6% per year. At the end of 1 year, Suzanne's investments earned $2,790. Find the amount that she invested at each rate. Okay? Now, this is an investment problem, but think back to the previous sections we've had. This is a mixture problem. Okay? We're taking investment and mixture and putting it together. Now, again, what I like to do is just give a very unique visualization of what's going on. So, instead of buying stocks or bonds or anything like that, think of investing with one bank and another bank, and then you're going to get cash out of the deal. Okay, I've had a lot of students. They're like, why are you drawing that stuff? But then 3 months from now, when I say the house problem, it starts jogging your memory. Okay, so drawing silly little visualizations like that can be really helpful to let this stuff stick for the long term. So what we have, let's imagine we're driving down the street and we drive past a bank. What do they usually have on their marquee? They tell you the interest rates that they're offering, okay, whether it be a loan or a savings account. That's what we're looking at here. So she invested $30,000, part of it at 11.5%, and another part at 6%. So one investment is 11.5%, and the other is 6%. Now at the end of this, she's getting some cash. And the amount of cash she's getting is $2,790. Okay? Now the only part of this that's missing is the amount that she actually put into these investments. She started with $30,000. Okay? They don't say that she put twice as much here or half here. They don't say anything like that. They just say that she has $30,000. So what we have to do is start by saying some unknown amount walked into that bank. But then the key word here, and I've said this in the past, the leftover goes here. So if we're talking leftover, it's the total minus the part that's already accounted for. Okay? And if you add those back up, you're going to get $30,000. If she puts 10,000 here, 30,000 minus 10,000, 20,000 here. If she puts 15,000 here, 30,000 minus 15,000 is 15,000 here. Okay? Now, this is going to go and model itself off of those mixture problems in the sense that we are going to, again, multiply this because we want to know how much cash she's making on this investment. If she's making 11.5% of her investment, it's 0.115 times the amount, so 1.115x, plus 0.06, 30,000 minus x, and then 2,790. Okay? Now, from there, we just go ahead and work that out. So what we're going to have, again, if these numbers, if you want to use your calculator, that's fine. 0.115x plus that 0.06 times 30,000 is 1,800 minus 0.06x equals 2,790. When you start adding a bunch of zeros here, make sure you are very careful when using this thing. Okay, that you're reading it before you hit enter and you don't miss a zero or add an extra one in there. Next, we've got the 0.115 minus 0.06 is 0.0 0.055 x plus 1800, and then subtract 1800, 0.055x, and then we've got 990, and divide by 0.055. Be careful with something like this. If you end up with a negative answer, you shouldn't be getting negative dollar amounts, okay? So if you do get a negative answer, make sure you don't just erase the negative and say it's okay. Sometimes there's a bigger issue. So if you see something that's not making sense, try and find your mistake. Okay? And then 990 divided by 0.055 gives you, come up here, 18,000. Okay? Now, 18,000 is your x. We put the x in 11.5%. So she is investing 18,000 at 11.5%. And then the remainder of it goes in at the 6%. And the remainder is found by taking 30,000 minus 18,000, which is 12,000. And there we go. If, when you set this up, you put x here and 30,000 minus x here, totally okay. The only difference is your x would have been the 12,000, and then 30,000 minus 12,000 would give you the 18. Okay? So there were 4 examples, but 3 ideas. Those distance problems, which again, create your table, find your scenarios that are within there, and then 1 category is given, 1 category is described. You combine those to get the 3rd. We then went to the value problems where there's 2 things, value and quantity. Okay, make sure you use those appropriately. And then we have these investment problems. And really these investment problems are mixture problems involving money. Okay, the big idea here that I want you to focus on are these initial setups, getting that equation down. There's a lot of important work that follows, but what's really should be your focus is setting it up. After that, it should be, just old routine from solving equations. Okay? So, as always, work hard. If you have any questions, let me know, and I'll see you next time.